Okay, good evening, and it's about the time, and let's go ahead and get this started. Okay, then I think that today is the last day of our class. Okay, so we've been having this class for last 4 weeks. Today gonna be the last day, and then it's a great pleasure for me to that have you guys in this class, and then most of you gonna continue in that next class, which gonna start even on Monday. This the second part of this same class, which is a continuation of this one, and then a continuation of the same textbook. Okay, I'm gonna send that syllabus for that class pretty soon, and then that class will be available by Sunday, and then we're gonna pretty much teach in the same format, and then same pretty much the same days, same times, and cover less material, and then I think we have to cover in that one 8 9 10 11. I think we have like a more time for us to that go through the material, because that each week we have to cover only one chapter, chapter 8 first week, chapter 9 second week, chapter 10 third week, chapter 11 fourth week, like that. That's the same book and the same kind of a material and same contents that we're going to expand that what we have been talking to another level. Okay, anyhow, that if we get back to what we have been doing, that I think in chapter 7, the last chapter, that we've just started that one last time on Monday, that and we covered up to a certain point, and then we were talking about the residuals of that particular model. In this model, what we did was, in the beginning we had an empty model or the null model, in which that the y variable, or whatever the response variable, whatever the outcome variable, being explained through the its own mean. That's called a null model or empty model. And then you check and see that if you model with that one, your predicted value gonna be that particular grand mean. Grand mean has been taken as your the predicted value, in which that we assume that prediction means like that if we hadn't taken the data, what your observation would look like, means the prediction. So we then what we did was, in that up to chapter 6, in chapter 7 we systematically included another variable called the x variable, or the independent variable, or the explanatory variable. In this case, that we added that categorical variable in, as an example, the gender. In that particular example, that the thumb length being explained by gender, like that. Okay, so good evening, April, and then we just started, and then we're gonna continue that what I've been talking about, and then
Okay.
okay. So then I just started. Okay, just
Okay.
started. Okay, yeah. So what I was talking about, that in the I don't know whether you're gonna take the next class. Are you taking the next one? The continuation of this one?
Yes, I am.
Okay, then yeah, that I mentioned about that one too. That because in that class, that pretty much that we have only 4 chapters to be covered: 8, 9, 10, 11. Same book, same textbook, same kind of material, and then we're gonna do the extension of where I stop from here, and then we're gonna start some Monday, and the
Okay.
class is available by Sunday, and then before that one, like maybe like a tonight or the tomorrow, I'm gonna send the syllabus ahead of the time, same format, same day, same time, same office hour time, pretty much same thing, same flexible that varying and everything, and pretty much everything the same thing, nothing gonna change. Okay, in that way you guys in a good shape. Okay.
Okay. Thank you.
Yeah, yeah. Then that if I get back to that, what I have been talking related to that, where I stopped last time. Last time I stopped that the getting the residual from the two group model, or the gender model. We call the gender model because in the beginning we have like an empty model, in which that we explain the y variable, whatever the variable of our interest. In that case, let's say for instance, the thumb length being explained by its own mean, which is the grand mean. Then later on, what we did was we check and see that how each and every observation is gonna be, away from that particular grand mean. That's called the residual. That's called the deviation. Then with that residual, we had like a plus residuals, minus residuals. We put together, the total becomes 0. To prevent that situation, we got the absolute value. Then we square that one. We were talking about so many things on that one. And then later on, especially that up to that chapter 6, we were talking like that. In chapter 7, I systematically introduced another variable, independent variable, x variable, or that's called the explanatory variable. And then in this particular case, that explanatory variable, I'm going to consider as like a categorical, or categorical variable will be taken into account for my explaining that response variable. So in that situation, that our equations little bit change. Then we had like a 2 groups in the beginning, like a gender, like a, for instance, if you think about the gender, I'm going to explain that the thumb length, then the gender has like a 2 groups, male, female, that they both groups. Within the groups, we have averages as well. So when we're going to find that residuals are calculated with respect to their own mean, not with respect to the grand mean, the way that we used to do that. So you're going to see some kind of some changes came along with that one when you're going to introduce another explanatory variable. That's what happened. So we had like a different discussion. Then we were talking about that up to a certain point, how to calculate the residual. See, so that's the point that we stopped last time, and then we can just continue that discussion from there, and then put in final observation. We talk about that one. We get that. Okay, I'm gonna go ahead and then share the screen, the next screen for you to see. Okay, share application. Screenshot. Yeah, so I did this one, then I was kind of like in 7.4, examining residuals from that particular model. Here, model means like we are talking about the 2-group model, okay? As we have said before, when we use a model to make predictions, our predictions are usually wrong. The residuals or the distance of each observed score from the prediction score give us an indication of how wrong our predictions are for each person. Yes, because that when you're gonna go ahead and look at that your observation, you see this is your observation. That's the predicted value for males. Sorry, females. This is for the females. See, this is 56. But when you go ahead and look at the average, if you add 56 plus 60 plus 61, then they divide by 3, that would give you this one. And on the other hand, for the males, they have their own average. 63, 64, 68 divided by 3 would give you this one. They're going to take their own averages, group averages, as their... Yeah. Group averages to that find that residual. See, residual is nothing but, see, okay, I hope it's okay. See, take the difference between these two, see, these two, these two, these two, these two, these two. So that's why here we were saying that see, that's not what we were expecting. We got like a different value. Okay. We calculate the residual from the empty model by subtracting the mean from each score. See, subtracting the mean means the grand mean from each score. We use the same approach for the more complex model. See, this called the complex model. The other one called the empty model. Using the model, we assign a predicted score to each observation. This time, however, the predicted score is not the grand mean for everyone, but one mean for females and another for males, as I mentioned. How do we quantify the residual from the empty model? Empty model, we know for sure. For each person, y minus y hat. Y hat is nothing but y bar. Y bar. Y bar means the grand mean. For each person, observed minus the predicted score. That's the same thing. This is called the predicted value. So see, the hat means the predicted value, y minus the predicted value. See, the both answers are correct. Okay. The same way, how do we quantify the receiver from the sex model? That one again, for each person, y minus y hat, we still use the y hat. For each person, observed minus the predicted score. The same thing. See? Same thing, but inside that one, inside that this here predicted value, y hat is nothing but y bar. Here y hat is nothing, y hat is not that one. Y hat is what? Y hat is, you have b naught plus b1 x. Here y hat is nothing but b, you can say b naught. See, that's the difference. In these both models, you have a different way of looking at this one. See, see, in the empty model, this one not connected. Yeah, the empty model, you have y equals y hat plus c. Y hat is, if you want, is y bar plus c, or b naught plus c. That means y hat is nothing but y bar or b naught. But if you go to that two group model, or we can say complex model, or we can say that yeah, complex model, then you can say y equals y hat plus c still. But here y hat is not like that. This y hat is b naught plus b1 x plus c. See, look at how I wrote it. Then where here also where y hat is nothing but b naught plus b1 x. That's the estimated value, estimated or predicted y. This is same thing, estimated or predicted y, which is in this case grand mean. See, in both case, that case we have y hat like this here. Okay, that's the empty model. Empty model has a y hat is y bar b naught. Two group model or complex model, you have a b naught, or sometimes in this particular model they call the gender model for that particular model. But in the general case, we can say two group or complex model. Only two groups. X has a two groups, where X has two groups. X, that's why we call the two. X is categorical. See, X cat for sure, and the groups will be that. See, X equals 0. The other one is X equals 1. As an example, you can say gender. In gender, you can say this one. They take like a male or female. Okay, I think let's say the female. Something like that. But they both the same. See, each person observed minus the predicted score. See, so the error is nothing but in both cases. In here, error. If you're going to take the error from this equation, you take the y minus y hat. See, y minus y hat. Same way from this equation. If you write from this equation, error is nothing but y minus y hat. I'm going to take this to the other side and put the negative. See? That's the same way you're going to find it. But both cases, physically you're going to call the predicted value, but mathematical wise, the notation wise, or the equation wise, not going to be the same. Here b naught only. Here b naught plus b1 times x. that complex model. Okay. So see, so notice that we use the same strategy to quantify the leftover error from any model. Leftover error. See, that's the leftover error from any model. We can do the subtraction in R just as we did in the empty model. We start with the tiny fingers data frame looking like this. It's a tiny fingers data. 6 people, thumb length, predicted value. You know how about the predicted value. We had that discussion. Okay. Then see, when we calculate the residual for each person by the subtraction, their observed score minus their score predicted by the model, we will save the results in a new variable of tiny fingers that we will call see sex.receipt. See, you go to tiny fingers thumb length, you go to the predicted value. Already you got the predicted value. You know how to get the predicted value. You know how to get this one, tiny fingers thumb length. Already you have. You got this one, and then predicted value, you put it over here. See, and now take the difference. That would give you tiny fingers. And then in the data set you have under this one. This is a new variable. See? That's the new variable. See? That's the new variable. See? This minus that, this minus that, this minus that. Now the grand mean. Grand mean is a different thing. We haven't calculated the grand mean yet. It hasn't come to the picture yet in this complex model. This minus that, this minus that, this minus that. If you add all these, see, 3, 3 get cancel off, minus 1 plus 1 cancel off, this is cancel off, they will add to 0. That's why we're going to square that residual, square or absolute value, we take that one. See, there's another way of you can get that one. You go to that model where you save that your linear model, and then you get the receipt function, run in receipt function, you can get that one too, and then put it over there and save to the same data set and call with the different variable, sex.receipt2. See, but you're going to come up with the same value. See? Compare the two variables, sex receipt and sex receipt2 in the output. Notice that we get the same values for this as we did for this guy. What does the receipt function in R do? See, compute the residual for all observation in the data frame. Take the model and compute all the residual or leftover variation. See, new word. Residual means a leftover variation from that model. That's the leftover variation. They're going to have explain the variation, but some variations cannot be explained. They were leftover. That's the leftover coming from that model. Leftover variation. Most of the variation we can explain, but some are leftover. That leftover gonna be bring it back, bring it to that is coming from that model. Okay, that's the leftover variation. See, that's what it says. Finally, let's compare the residual from the tiny sex model. I mean, like to those from the. I don't know this one. Finally, let's compare the residuals from the tiny sex model to those from the tiny empty model. See, I have a tiny empty model. That means without including X. This one with including that one. Let's first add a variable called empty pred. See, prediction, using the predicted value for this one. And print out the tiny fingers again. We could have called this variable anything. The point is to name is something meaningful. So in the case we call it empty pred, short for predicted from the empty model. See, predicted from the empty model, predicted from the empty model. Okay. See, we calculated that one from the empty model. You go to the tiny empty model and get the prediction and then put it back into this one. See, that's 62. This is 62. This mean is 59. The male's average is 69. Female's average is 59. Male's average is 65. Grand average is 62. 62. See? Now use the receipt function to create a new variable called tiny fingers data from the empty residuals. Now you want to find the empty residuals. See? You can find the empty residual and put it over here. See? How do you do that? See? You go to the receipt. See? Empty receipt. Empty receipt. use the residual function and then put it back into the tiny fingers data set. So you're gonna get see. Something. So I'm not working. Okay. I think. Let me see something wrong with this one. See, the page not scrolling, got frozen. Let's see. Yeah. See, okay, I'm gonna go back to. I have that issue all the time with this. It's like the browser has issues. Microsoft Edge. It's not a good. Microsoft, they don't do a good job all the time. Browser has some issues. Let me see. What's that? Some go away. Close this one. Close this one. I'm gonna open a new one. Okay. Okay. See what happens. Okay. 7 4 7 4. This one. You get the residual for the. See, generate residual from the tiny empty model. See, tiny empty model. Print tiny fingers. See, let's get this one and run. Tiny fingers. Oh, we can get the head. Tiny fingers only 6. Okay, we don't have to worry about that one. See, residual. And get the residual from the tiny empty model and then put it back into the tiny fingers. And run. See, it's a predicted value. Doesn't matter whether we have a predicted value or not. We can easily get the from that this model, the residual. There are 2 ways we got that one. The other one, predicted value, we have here or not. See, look at their residuals. You see, it's the same thing. This is the original data set. This is the data when fitting into the empty model. See, this is the predicted value. This is the predicted value when you fit into the two group model or this complex model or that this gender model. See, this is a predicted value. This is the residuals when you're going to fit into the empty model. These are the residual. Either one of these going to be the residual when you're going to fit into the gender model or the complex model. See, look at the residual. See, earlier, see, residual. See, the distance 6, now it's 3. See, like that. See, some places you have a higher value, lower value like that. See, some 3 most of the time. See, but here, see, 2 sometimes. Okay. So compare the two columns of the residuals, sex residuals and the empty residuals. Oh, I'm sorry. Yeah, I just see this one. This the code I wrote it. See, yeah. Thank you. Yeah, see, this is resid tiny empty model. Empty model. When you run that one, and then I got the tiny fingers. It has only 6 data points. This is the original data. That's the original data. That's the original data. This is the original data. This is the predicted value for the empty model. Empty model. These are the predicted value for the gender model or the complex model. These are the residual for the empty model. These are the residual. Either one of these residuals are for the gender or complex model. See. So they're going to say that compare the two columns of residual. That means sex residuals, which is this resid and empty residual. See. What is the difference between sex resid and empty resid? Okay. The categorical variable, but empty resid is a quantitative. No, these are not. These are two answers. Resid is the leftover variation from the sex model. That's the leftover variation from this is called the leftover variations. That means some variations by this model, most of the variations being explained, but still something is left over. Some you cannot explain. That means that this point is not completely on 62. Your 56 point is not on 62. That's why that variation. But some variations you don't have that been explained by this guy. See? But once you have this one, this gap is the variation. That's the leftover variation. See? That's the leftover variation in the empty model. See? See? If it is sex resid, it's the leftover variation from the sex model. See? This one. It should be on 59, but your data observation is 56. See? It's 59. See? So therefore, those are called the leftover variations from the sex model. But the empty model resist is the leftover variation from the null model. That's right. These empty resid are the leftover variations from empty model. These are the leftover variation from the sex model. And sex resid represent the residual left after subtracting our sex model. But empty model resid is a residual left after subtracting our null model. See, sex resid represent the residual left after subtracting our model. Subtracting out our model. Subtracting out our model. See, subtracting our model. See, we subtract. Subtracting out our model. But the empty resid is the residual left after subtracting out the null empty model. See? The same null model. And null model, my data point minus the null model. See? Subtracting that one, you get the residual. Or you can say that's the leftover variation. That's the leftover variation, or the sex model and the null model respectively. That means like a sex resid and empty resid are the variation, leftover variation from sex model and the null model respectively. Or So sex resid and then empty resid are the residuals left after subtracting out sex model, and then residuals left after subtracting out null model, respectively. So based on the rex resid and empty resid, which model has more error around it? You see, the tiny empty model, because the residuals are greater, they see in extent from that model. See, look at the residuals. Empty model has more error. See, more residuals, more deviations. See, which model has a more error around it? See, this is the one. The empty model has a more error around its model. The model is this one. This is the model. 62 is the model. For that particular data point, 62 is the model. Then how much the error would be? 6. See, but according to this model, 59 would be your it has come down a little bit. 59 would be your model. So you take that gap. See, that's why they say that empty model, because the residuals are greater in extent. See, more error around it. See, you have a less around it. This model. If you use this model, your error would be around 59. Then that when you are, whereas that when you are using empty model, your error would be around 62 for the same 56. It's not going to change. This change now 59, earlier 62. Look at the error has reduced from 6 to 3. But when you have an empty model, your error around that one is far more than you have that deviation around the this one when you run the the sex model. That's the reason that what it is. Now you're going to graph that residual from that particular model. You might be wonder why we bothering to generate and save residuals. We will have a lot more to say about this later, but the short answer is it helps us to understand the error around our model and often suggest way of improving the model. See, that's the reason that we're going to put heavy weight on this error. Just as the first things we do when looking at the data set is to examine the distribution of the variables. See, we're going to look at the distribution of the variable. It is good to get the habit of examining the distribution of residuals. That's my variable now. Residual would be my variable after we fit a new model. See, let's go back to the full fingers data frame. We fit the model lm thumb, see, tilde sex data fingers, and save the model into this object. Using the resid function, we write some code to generate a new column in fingers called the sex resid, the residual from the sex model. Store the residual from the sex model. See, residual. You need the residual. See, you need the residual. You need this one. But this time you're not going to use the empty model. You're going to use the sex model. Okay. So Control V. You have a resid. Tiny. They say that let's look at the full model. That one called not the tiny, you call the empty model. See, that one called get it from the resid, and then save that one to sex model. See that model, and then this has already run. This part has already run, and then it has been saved to this one. That's the one I'm going to utilize in order to check get the residuals. And then I'm going to create a new column called the sex resid and put this one. And then print this first few rows of that one. Head, select, I'm going to select the fingers, thumb, sex resid, this one. 3 variables and 10 entries. Thumb length, see, there resid. Thumb would be this, and the 2 variables are shown on this one. This is the way the data set, name of the data set is fingers, data frame, then thumb, then sex resid. This is the real value. This is the residual. It's a residual. In the following window, we have provided the code to create a density histogram of thumb in a facet grid by sex. Try modifying it to generate density histogram of sex resid in a facet grid by sex. Okay, compare the histogram of residual from the sex model with histogram of the thumb length. See? So we have the density histogram for thumb, data, fingers, facet grid. See, by this one. In the following, we have provided the code to create a density histogram for thumb in a facet grid by sex. Then try modifying it to generate density histogram. Density histogram of sex receipt. We don't need for this one. In a facet grid by sex. See? We don't need for the thumb. We need that histogram for this guy. Residuals. Okay. So I'm gonna say text part receipt. That's the data set name, still the fingers, and it has been drawn with respect to gender again at a facet grid. It has been faceted. See, column wise. See. See, I have this. See, more jagged. There are no very smooth shape. Okay, in order to get the smooth shape, you know what you are supposed to do. You are supposed to have a more data. The larger the data set is, that more accurate, that more smoother that your distribution would be, not jagged like this. Okay, so this is for error. See? And you have to notice something very clearly. Its mean should be 0 always. Error has a mean of 0. You know that. If you add all the error terms for any data set error, they would add to 0. So your average is always 0. See, you're 0. It's been centered around 0. Okay. In the activity below, we have depicted the density histogram of thumb by sex in black and next to the histogram of sex receipt by sex in sky blue. See? This is for the thumb length. This is for the residual. Okay. So this is the one I drawn, that one, but they have used different color. Doesn't matter. This is for the thumb length and this one for this one. What do you notice about these pairs of histograms? These pairs of histograms, this pair and this pair. In the thumb histogram, it seems like the males are shifted higher than the females. Shifted for the males. But that is not true in the sex receipt histogram. See, in the video, there's no such shifting. In both cases, there will be rounded, so they're clustered around its mean, which is 0 in both cases, male or female, regardless of the gender. See, that's what it says. We can add the means of the thumb for females and males to the thumb histogram with some R code. First, we calculate the mean thumb length for each sex. See, group and save it in R object called the thumb stat. See, you're gonna get the favorite statistics. See, favorite statistics by thumb, by this one. See, then get the favorite statistics, and we can chain that one. See, you get the thumb stat, and then you're gonna draw the density histogram. See, for thumb length. Here we have provided the code to add mean lines for each sex group to the thumb histogram. Modify the next chunk of code to add mean lines for the sex groups for the sex receipt. See, this one not for the thumb. We need that one for sex receipt. By this one, data fingers and favorite statistics of that one, and this one, save, but that one. Then we're gonna get this one, now the thumb step. And the mean of thumb length to 4. See, receipt. Okay, residual stats. Which line? No, sorry, the create histogram, the line and the mean of thumb length. Let's keep this one for thumb length. Okay, sorry, thumb length. Okay, the other one. Keep as it is for thumb, and the other one let's use that one. Thumb for this one also thumb. Okay, this is good. Okay, this one mean color blue and data thumb stat. Okay, modify this code to add lines to present the mean sex residue each group. See, we call this one not the thumb, they call the sex receipt stats. So sex receipt, sex data fingers, GF histogram, sex receipt data fingers. Modify the next jump code to add mean lines. Okay. So I said, okay, this one, this is the one they want us to add. Vertical line, x-intercept, gonna add the mean, color, thumbstat, not the thumbstat. Its name is dot receipt stats. See, receipt stat. Then run. That's the last one. There are two, okay? Two sets. Previous one black and this one, that's for the thumb, this one. See, look at their lines. This one is like a shifter to this one. They have a higher value for the average, see, for the males, thumb length. But when you're going to go ahead and look into that, this one, they both would carry a same cluster around the center for their residuals. See, their residuals. Their residuals. See, right there. Above in the histogram of the residual in the sky blue, why are the means of sex receipt for the two groups not different anymore? See? Because the residual law, what is left over after subtracting the means of the two sex groups from the original thumb lengths. With the residual law, what is left over after subtracting the means of the two groups from the original thumb lengths. From the original thumb lengths, you're gonna subtract. Okay, in this case, female, you go to the female. There are three female. You're gonna go to their data, three data set, and then you're gonna subtract its mean from their observation. That would give you 0. So does with the other group. Because the residual law, what is left over after taking out the effects of sex? Yeah, see, because the residuals are what is left over after taking out the effects of the sex. That means that you're going to take the subtract between the observation and their own mean. Because the residual law, what is left over after accounting for variation in sex. See, that's another way to look at it. Accounting for that leftover variation. See, it's the leftover after taking effect. See, residual law. Because the residual law, what is left over after modeling the data with sex model. See, that's another way to look at it. And all above are true. That's why they all are true. See, that's why this one has like the same 0. They both would act pretty much when it's come to the residual, regardless of the gender. They both sets acts pretty much the same fashion. Okay, that's right there. Above in the histogram of the residual in the sky blue, why are the means of sex receipt for the two groups are equal to 0? You know why is that? Because even the mean of bunch of residual is still a mean. Mean always balance the residual. We talk about that. Mean always balances the that residual, adding them up to 0. That's why 0. Residuals always. This group residual and this group residual. If you go ahead and check the residual for this group, that's nothing but observation minus its mean. Observation minus its mean. Observation minus its mean. If you add those three, see, you add. See, those are. See, come to 0. See. So all together, you're going to consider all together, see, and then here even see, and then on the other hand, you go to this group. Look at this group, -3, 1, and plus. I'm going to go here, see, female group, 0. See. This group, male group, add all the residuals together, 0. And add all the residuals together, again 0. Doesn't matter. That's why this always 0. This one is 0. This one is 0. This one is 0. If you draw the histogram for the overall one, overall residual, still 0. Still 0. See? Still 0. Excuse me. Female group, 0. Male group, 0. See, add together. -3 and +3 get cancelled. Minus 3 and plus 3 get cancelled. And on the other hand, for the even the grand total, still the 0. But that's not the case when it comes to empty model. Empty model, we don't have a two categories. We have like a just like empty. There's nothing being added on, just an average. It's average with respect to the average. The residual is going to be added to 0. See? So in the male group, female group, average is 0. Male group, average is 0. Overall, if you draw the residual, still 0. It will be centered around that. See? That's the reason. See, now you're going to calculate the sum of squares, empty model. See, you can remember that how you calculated the in the empty model, how you calculated this one. See, ANOVA, running ANOVA, can you remember? See, calculating sum of squares. Sum of squares means here in the textbook they say SS. We're going to call that one SS residual. So SSC, we have a name, sum of squared residual. Sum of squares, sum of square residual, sum of squared error, sum of squares, or simply sum of square. Okay. Residual actually. How do you get look into the residual in another way? See, look at sum of squared residual. So residual sum of squares, residual sum of squares, or square sum of squared residual. You can read from here to here or here to here, 82. What that means, you see, remind yourself how to use the ANOVA. See, LM, you run this one, you put this one. See, write the code. Write the code to get this one means like you're gonna write code over here. You go to ANOVA, and inside you run this tiny empty model. That would give you this one. See, residual. We talk about the degrees of freedom, independent that pieces of information. Independent pieces of information is nothing but n minus number of parameters to be estimated. Number of unknowns. Number of unknown in this case are only the grand mean. It's unknown. That's why you calculate that one. You have only B naught only. B naught only. That's why you're going to subtract 6 minus 1, 5, 82. Since this one is 82, this means nothing but 59. This is nothing but your data minus the 62 and then square and then sum them up. That would give you 82. See, that would give you 82. We saw that how you got that. And then this divide by that gave you 16.4. See? These two, we're going to come back to that now pretty soon. See, what would be another way to calculate the sum of squares? Sum of squares, you can go to, see, tiny fingers, go to residuals, you can square and sum. You go to tiny fingers, empty residual has been already added to that one, the residual, you're going to square residual. Up to here, same thing, okay, you don't have to put, if you want, you can put a parenthesis again, but from here to here, same thing. They were mainly focused on empty residual and square and sum them up. What is the unit for SS? See, millimeter squared. That's not important. It's okay. Now we are trying to calculate the sum of squares for this model. Okay, let's do the same thing for this model and then run and see what you're gonna get. And now, so the for this one they don't give this one. We're gonna empty model, they were not there because we're gonna need the tiny other model, tiny 6. Okay, let's run this one. See, now 2 lines, not only residual, it's gonna have this one too. See, 2 rows now. See, 2 rows, and more material, more numbers being added, more numbers added, something over here too. See, we're going to talk about all these. See, not only residuals, there's something called the model. See, in the output above, which row is the error leftover after fitting the sex model? The leftover after fitting this model, the leftover variation is called the row that say the residual. This one, see, look at what happened to sum of squared residual has gone down to 28. and the other part goes over here. But if you add these two, it's again how much? 82, same as what we had here. See, whatever the residual you had, sum squared residual in empty model, now being split into two parts. Now two parts. How? One gonna go with this model, the other one gonna go to the residual. See, 28 and 54. How this happened? We have to just little bit looking into how this happened. Okay, I'm gonna little bit do this one in detail for you to see how we got this one, then to get a clear picture. We can run that program and get that one, but you get a clear picture by looking at these numbers. You can remember if I go to the empty model. Okay, I'm gonna connect this one. Okay, you have an empty model. You have empty model. Okay, you have an empty model. In the empty model, you know how we saw that. See, we have a y bar. Okay, we have a y bar. Y bar was 62, if I were right. It was 62. This is nothing but b naught. It's nothing but y hat. Same thing. And other points you have. You had 56. See, 56. I'm gonna a little bit separate it. Okay. Then you had a 60. Then you had a 61. Then you had a 63, 64, 63, 64, 68. I separated. There's nothing on this one. Okay, I'm talking about the empty model. So then you calculated this one. That's called the error. Can you remember? You get 56 minus 62 square plus. In order to prevent the negative, you square that one. And then that will be added to the next one. 60 minus 62 square plus. Then 61 minus 62 square plus. Then 63 minus 62 square plus. 64 minus 62 square plus 68 minus 62 square. This summation we call the sum of squared residual. Residuals. In the books, they denoted this by SS. We call that one SSR, or sometimes I call this one SSC to say SS sum of squared error. And then if you go ahead and then check 156 minus this one minus 6 squared plus, see, minus 2 squared plus minus 1 squared plus, see, 1 squared plus 2 squared plus 6 squared. Then let's square this one. 6 squared, 36 plus 4 plus 1 plus 1 plus 4, 36. 36 plus 4, 40, 41. Another set like that, then 82. That's how you get the 82. See, that's why we have 82 here for the empty model. I'm talking about here. 82. Sum of square residual, 82. 82. And in our model, this is my model. Model is nothing but y equals y bar O v naught O y hat. See, I have only one parameter. Therefore, degrees of freedom. See, df, degrees of freedom, degrees of freedom for residual, nothing but n minus number of parameters. I'm going to say okay, number of parameters. N is the sample size, which is 6 minus 1, 5. See, you saw that. Then later on, we were talking about the mean squared. See, something like this. See, mean squared. Mean squared is nothing but, see, mean squared residuals. I call that an MSR or MSE. It's nothing but sum of squared residual divided by degrees of freedom of residual. I'm going to say E to indicate residual. See, df of E, error, or sum of squared error divided by degrees of freedom of error. This one is nothing but 82 divided by 5. See, that's how you got this value, 16.4. 16.4. Now we're going to have, not that one, now we're going to have a complexo two-group model, two-group gender or sex model. See? In that one, if I draw, you're going to introduce for x, see, x variable. You have a y variable here. Earlier you have y only. Let's say here y is thumb length only. Thumb length. Okay. Now I have a thumb length and being explained by another variable, categorical variable, which is gender. Gender has two options. See, female and male. Again, I'm gonna keep this one grand mean, but it's not my model this time. This is y bar. Y bar is 62. It's not b naught. It's not y hat. See. Now I go over here under this one. I have a. I'm gonna a little bit separate for under this one. Okay. I have a 56. I have a 56. Then I have a 60 and 61. 60. I'm sorry, 56, 60 and 61. Yeah, 60 and 61. Okay, for the female. For the male, I have 63. Rather than like they're gonna have like I'm gonna draw like a jitter plot. Okay, not like a scatter plot. A scatter plot, oh, sorry, point plot. Okay, little bit spread out. 63, 65, and 68. At the same time, I'm looking for its own mean as well. Its own mean would be how much? 59. 59. See, somewhere here. See, I have another line. 59. See, this is nothing but y bar of female, which is 59. That's my y hat at a certain point. At a certain point, that's my b naught. See? So it's a similar fashion that for the 64, this one, I'm sorry, this is 64. This is not 65, 64, 63, 64. Let me see. Yeah, 64, 64. Then your male's average would be y hat for male is 65. See, that's 65. That's nothing but you can say y hat for that one too at a certain point. And then if you get that difference, I'm talking about this line, this line, and this line, that difference is B1. That difference is B1. Now what we're gonna do, in order to find the error, sum of squared residual, this time we're gonna find in a different way. We have to find several things. One is, look at your data point, how it's been deviated from the grand mean. That's a one discussion. At the same time, how that been deviated from this own mean as well. Okay, we're gonna look into two things. So that last time, when I write that sum of squared residual, I'm gonna go back to here. One more time, come back. And I'm gonna write something here. Summation of y minus y hat square. See, that's a formula. See, SSR or SSE in the empty model is, that's the formula. See, y minus y bar squared. That's how we got that. This time, how do you get the SSR? Look at how I'm gonna get the SSR. SSR I'm gonna go to my data point for the male. For the female 56, I'm not gonna subtract that grand mean. I'm gonna subtract its own mean, which is 59 and square, and go to the next entry. 60 minus 59 square. Okay, and plus, then go to the next entry. 60 minus 59. We're done. Plus, that's for female. That's for female. Females. But you have to keep adding, and the males should be taken into account too. Now I go to the male. 63 minus 65, not the 59. See, I'm gonna subtract its own mean and add to next entry. 64 minus 65 plus 68 minus 65 squared. Okay, let's go ahead. 56 minus this one, minus 3 squared. 60 minus 51, minus 1, sorry, plus 1 squared. Okay, plus 1 squared, plus 2 squared, plus 63 minus 65, minus 2 squared. 64 minus this one, minus 1 squared. 68 minus 65, 3 squared. So let's add 9 plus 1 plus 4. 4 plus 1 plus 9. So 9, 1, 10, 14, 14, 14, 28. That's how you get the 28. The sum of residual when you run the other one. See? So that's how you get the residual. Okay. Then, if that's the case, the formula for this one, if I write as a formula, I'm going to write as a formula. If I write as a formula, it's nothing but, I would say, sum of y minus, see, y, I would say female y minus its female y bar, see, square, plus male y minus its own mean y bar square. See, it should be like that. That's how you got the SSR or SSE for the group model. See, I wrote the formula. I without utilize I'm in a certain way I'm using the formula here. These are for the males, but I didn't go with that one. I didn't use the formula and then use that one. I that physically just showed you that how those are coming, and then this is the mathematical formula. Your female y values should subtract from its y bar and stop it, and then go to the males one and subtract and add together. That will give you 20. And now I have another one, very important one. It's degrees of freedom of residual or error. It's nothing but, as I said, n minus number of parameters. See, I told you already, number of parameters. Now you know in our model, okay, the group model is like this. See, our model y equals b naught plus b1 x plus e. You can remember your empty model is nothing but y equals b naught plus e, or b naught is same as y hat. Okay? Here in this case, b naught and b1 is different. But what I'm trying to say, this time you have a two parameters, b naught and b1, two, b naught and b1, n minus 2. What are those? b naught and b1. That's why when you have a 6 minus 2 should be 4. See, it is a follow. That's the reason. 6. Now That's sum of square residual. That's not the case that here. There's another one called this one. Sum of squared x means the sum of squared model. New thing will be added to this one because of this new model, another variable being added to this one. Some variation is going to go to that one. Okay. So this one, I call this one SSR, or I'm going to write this one again. Sum of residual sum of squares. Okay, residual sum of squares, or residual sum of squares, that's the same thing, or squared sum of squared residual, either way. Okay, residual sum of squares or residual. Okay. The similar fashion, I'm looking for something called models. Sorry, I'm going to go to residual, not the residual. I did the residual. I'm going to go to something called the model sum of square. Model sum of squares. Model sum of squares, or sum of squared model, which is denoted by SSM. How do you get that one? In order to get that one, what are you going to do? You're going to go ahead and go to the male, females, go to their mean, which is 59, and subtract 62 and square. You go to their mean and subtract the grand mean. How many times you have to do this one? That's for the first individual. This for the second individual. This for the third individual in that female set. That's for the female. Up to here, female. Female. Plus, I keep going. Now I'm going to do the same thing for the males. The male has a 65 minus the grand mean. See? 65 minus the grand mean for the second individual. Same as second male. 65 minus 62 for this one. See, that those are for the males. I'm going to add all these together. This time I was looking for the difference between the means. Difference between the means. See, I'm talking about here. I'm talking about this gap. See, this gap. No, I'm sorry, not this gap. This gap, not this one. I'm talking about this 156. Okay, I'm talking about this line. See, this line and this line for that individual. Again, for the second individual, this line and that line. And third individuals, this line and that line. See, that's the model. And the same way, then I go to the mean. Okay, and the grand mean. See, for this individual, I'm talking about for this individual, this mean and this mean. For this individual, this mean and that mean. For this individual, that mean and that mean. See, that's what I did. For the residual, I did a different thing. For the residual, I did the data point minus its own mean. Now mean to mean, mean to group mean to grand mean, group mean to grand mean. Okay. So then you're going to have here minus squared, minus 3 squared, minus 3 squared, plus 3 squared, plus 3 squared, 3 squared. Then you have what? 9 plus 9 plus 9 plus 9 plus 9 plus 9. 54. 54. That's how you get the 54. Okay. Then again, that's called the SSM, sum of squared model. If you write this one as an equation, this is how you're going to write. It's nothing but you're going to write this one y Write it clearly, okay, for you to see. You're gonna write this one. Y bar female minus y grand mean squared plus, see, y bar male minus y bar squared. See, that's how you got that. The earlier y minus, see, earlier, see, the entry minus y bar, not the bars. See? This time y bar minus grand mean squared plus y bar minus, keep going for all the both groups. This for the first female, second female, third female. This is 59 still. See, this one. And the first male, second male, third male, 62 this one. 62, okay. The same one count, because it doesn't matter whether what value for the your observation. It's about that the difference between the grand mean and the group mean for males and females. See? And the other important thing is the degrees of freedom of, see, model. I'm going to call that one this one. See, degrees of freedom for model denoted by DFM. Similar fashion, if I write over here, degrees of freedom for error or residual, let's say error or residual or deviations. Okay, deviation doesn't matter, same notation. I'm going to say DF subscript E. Okay. For this one, how could you going to find the degrees of freedom? This is see, same one. See here on. See, by one. It's very easy. We can say number of x variables. How many x variables we have? Only one, which is x for gender, which has two options, male and female. That's why it's one. That's why it's one. Then you know the other thing that the related to this one, if I go back to this one again, that residual back again and get the mean residual. Sorry, here I'm going to write something to over here to mean squared residual, the other part. Okay, mean squared residual here, mean squared residual, which is, if you want, you can say mean squared residual is nothing but sum of squared residual divided by degrees of freedom of error, which is 28 divided by 4, which is 7. It is 7. You saw that one, 7. 7. This one is nothing but, it's called the means. See, mean squared residual. This one we can say mean squared model. Mean squared model is nothing. Now we're going to put on average what would be the mean squared model is nothing but sum of squared model divided by degrees of freedom of model. Sum of squared model is nothing but 54 divided by 1, which is 54. And then you have something called the F value. F value is nothing but F value. That means it's going to be distributed according to F distribution. F value is nothing but mean squared model. Mean squared model I'm going to denote by MSM. Mean squared model over mean squared error. Mean squared model is 54 and mean squared residual is 7 divided by 54, which is 7.7143. 7.7143. Not only that, they think this ratio distribute. We're going to talk about that one in next class. This ratio distribute according to some distribution, not the normal distribution, not the bell shape. Very right skewed distribution called F distribution. See, like this. This is F. F is nothing but mean squared model divided by mean squared residual error. That is distributed according to right skewed distribution called the F distribution. F distribution. They say that if that's why it's called the F value. F value means that's the observed value. I'm going to observe somewhere here. Let's say my F value is this one. F value, that one I would like to call the F naught. F naught in this case would be observed value. Observed F value would be nothing but mean squared model divided by mean squared error, which is 7.7143. They say P value is nothing but the probability that the area to the right of that value, this area, in that particular distribution. This is what we call the P value. P value is probability that F greater than F naught. They have calculated that one for us. That means probability means the area. Probability that F greater than 7.714. In this case, they say that one is 0.0995. 0.04995. See, I'm gonna get this one to here. 0.04995. See, let's call it P. That's how they are related. See, they put the star. Star means what? Almost 0.05 round. You can consider this one as a 0.05. See, if you have a dot 0.1, double star 0.01, triple star. See, so, codes. Okay, sorry. This 0 you have a triple star, 0.0001 you have a double star, 0.01 single star, 0.05 you have this dot. How come the star? Star, one star, 0.05. It should be 0.05. First, 0.01. No, not the 0. Okay, oh, I'm sorry. This is what they were trying to say. This is in between 0 and 1. In between 0 and 1. Okay. This is in between 0 and 1. So this one 0.001, see 0.01, 0.05, dot 0.1, right there. Yeah, see, that's how we got this one. But still, we are missing something. Still, we are missing something. We know that one. We have a 82. It doesn't show here. See, where is 82? Where is 5? This one. It is not residual when it comes to this for the model. This is for the. This case come for the empty model. But when you add still, it should add to what you had for the empty model. That's an empty model playing a heavy role. Look at that, these two, sum of squared of model and sum of squared residual. They would add to something called 82. it has a name at this stage. That's called the total sum of squares. Total sum of squares. Let's see what that means too. And then let's see how to get that one to be displayed too. So the third one is I'm looking for, okay. Then I have a residual sum of squares, okay. If one residual sum of squares, then I talk about its degree, SSR, SSC, its degrees of freedom. Then I got the mean squared residual, and which is 7. Then I talk about second part, model sum of square. I got the SSM. Then I went to its degrees of freedom. Then I talk about F naught and the T value. Okay, this P value. Then third one, actually, that something is missing over there called the total sum of squares. Or squared sum of squared totals. Sum of squared totals, which is denoted by SST. How do you calculate that one? Let's see how to calculate that the total sum of squares. What are you going to do in order to calculate that? Which one and which one? SSR, total sum of squares. We're going to go back to this picture. Nothing but 82. So, no, this one. No, not this one. See, this one. You got the difference between what and what? 56 to its mean. Then you got the difference between that to that. Okay, this is what I'm talking about. If I go back and tell, you got in the beginning this gap. Later on, you got this gap for that entry. Same way, you got this gap. I'm going to a little bit shift it up. This gap doesn't matter. Okay. It's not clear. See, I'm talking about when at the 60 for my convener, I'm going to lift it up here. Okay. So 60. But this line is 59. You know that one. I'm going to put 50, 60 over there. That's 60. I got 62. 59. It's on me. Later on, I got its mean to grand mean. I did that one. See, I got that back too. I got this gap and I got this gap. See, for that entry. Then I went to the male side, 63. For the 63, I got this guy. That's the difference between the mean, grand mean, and their mean. And at a certain point, I got the 63 minus 59. See? And I went to 64. I got this one, mean to mean, and data to mean. So, and at a certain point, I got the mean to mean, and I get the data to mean. Data to mean called the residuals. Mean to mean called the model in another way. Now I do what? Look at this point is more than enough for you to see. I'm gonna go from point to grand mean, which we did in the empty model. See, point to grand mean. See, look at the 56. Look at the others are added. Okay, then point to grand mean. Whether subtract or add doesn't matter. Point to grand mean, which means that's called the total sum of square. That means go to each and every one. And I had a 56. 56, okay, 56 minus 62. 56 minus 62. We already did that one. Then I'm going to go to the next one. Doesn't matter, regardless of that entry. 60 minus 62 square. And the other one, 61 minus 62 square, plus 63 minus 62 square, plus 64 minus 62 square. And then 68 minus 62 square. We had all these. This one minus 6 squared. We did this one for the empty model. We had that one. And plus minus 2 squared. Minus 1 squared. Plus 1 squared. 2 squared. 6 squared. we have a 36, we have a 4, we have a 1, we have a 1, we have a 4, we have a 36, which is 82. This is nothing but sum squared total. As a formula, if I write y minus y hat squared, see, y minus y hat squared, you can simply call y. You don't have to say y male or female to distinguish. See, that's the total sum of squared. That's 82. Then we have to go and look for its total, its degrees of freedom of totals, which is I denoted by df subscript t. How do you get that? See, you can subtract always one is n minus 1 minus 1. See, you don't have this one. See, 4 plus, see, 4 plus 1. 4 plus 1. 5. You don't see that one here. There's a way to get that one displayed, okay? But then you have a 6 minus 1, which is 5. See, which is 5. Sorry, for that one you don't need to that mean squared value. You're not gonna looking into that one. We're gonna looking into that one later on. But if you want, you can get the total divided by its degrees of freedom. See, then you can go and get a mean squared total. See, mean squared total, mean squared t. It's nothing but sum of squared total divided by degrees of freedom of total. 82 divided by its own 5, 16.4. We had that. See, if you want, you can put that. See, those are the that means eventually that means SST total sum has been decomposed into sum of squared model plus sum of squared error. That's what they say. See, it has been split into like that. See, it has been decomposed. See, so nothing but summation of y minus y bar squared has been split into. You can remember that model, how I wrote for the model. For the model, I say that summation y bar m minus y grand mean squared plus, okay, summation for the whole thing. Okay, I'm gonna put like this. Then y bar female minus y grand mean whole thing squared, see, plus that's the SSM. Then the other one I wrote this way: y minus y bar f squared plus, that's for the female, y male minus y bar male squared. See, okay, that's the way. If you want to write the equation wise, you can write that one, or this has been decomposed. These two add together, you can get that. See, that's the way how it has been happening. Okay, that's how this split come into the picture. And then later on that we talk about the F, and then I'm gonna talk about something before we do. We're gonna talk about that one later on, but I would like to talk about that one ahead of the time. Something called PRE. PRE called the proportional reduction in error. It's nothing but sum of squared model divided by not SSE, SST, total sum of squared. You can remember SSM divided by SSE is F. Actually mean squared divided by mean, this one is F, but this time SS sum of squared model divided by this one. In this case, it's going to be 54. Total is 82. If you divide, you get 0.6585. See, 6585. How much error being reduced due to the introducing a new variable? That's the meaning of that one. How much it has reduced by 65%, no, as a percentage. Earlier you had 82. See, this is the unexplained variation. But due to that, this variation, due to this model, because of the model, going to explain 54 of them. In that way, that's a good explanation. Explain that so much of variation left over from the, this the variation left over from the model. Can you remember? This is the leftover variation from the empty model. Due to this model, due to this two group model, or due to this introducing a new regressive variable, sorry, that gender categorical variable, or that down the road we can even extend the same idea for even the quantitative variable, doesn't matter. Because of the variable, this has explained 54 that this is how much that error has been reduced due to this model, due to the, not the empty model, I'm not talking about empty model, due to the other model, SSM. That's called the pre. Okay, that will be displayed over here too down the road. Okay, we will be displayed over there too. See? SSM. See, in another way that SSM, that you can looking into that one, that if you go ahead and look at this one more time, more carefully, you can see that one down the road, that when we come to that, even when display the total, okay, you can see that one too. Even though I talk about that one, I'm going to get back to that one again too. But because of that, if you want, I'm going to go to F again. F is nothing but mean squared model divided by the mean squared error. We know that. I'm going to little bit adjustment I'm going to say this is nothing but sum of squared error divided by degrees of freedom of its own. And this is sum of squared mean model divided by degrees of freedom of m. This one is equal sign. This is sum of squared model divided by degrees of freedom of model is called the mean squared model, and divided by sum of squared error divided by the degrees of freedom of error. You can rearrange like that. Okay, so you know that. Okay, then sum of squared, then what I'm gonna do, I'm gonna divide this by SST and divide by degrees of mean separate. Okay, see, you have that one, and I'm gonna divide the numerator and the denominator by SS total, SSE divided by SS total. See, and it's being divided by its own degrees of freedom. See? SSE, SSM divided by SST is nothing but pre. See, this part is nothing but pre. See? So I'm going to say that pre divided by degrees of freedom of m divided by SSE. SSE I'm going to write with the aid of total, SST minus SSM. We know that, divided by SST already we have this one. I did the adjustment. I am going to call the SSE is nothing but SS total. SSE nothing but SS total minus SSM. If you go to this side, that's what I cannot little bit. So the adjustment. Then I'm going to write whatever I have for the numerator, which is free divided by degrees of freedom of model. Then the denominator, I have whatever I have, I'm going to split SST minus SSM over SST in degrees of freedom of error. See? This one is nothing but F still. See? Still F. See, I split this divide by that, this divide by that, and divided by whole thing again by degrees of freedom. Divided divide by divide and again divide, and divide by divide, again divide. That's why I put the slash to indicate like that. Okay. So see, then we can say 3 over degrees of freedom. This one is nothing but 1 minus this part is again what? 3 divided by degrees of freedom of error. See, F can be written in terms of 3 as well. See? Like that. If you want, you can write like that. We can have a discussion a little bit further down. But this is the design. But as I said earlier, you don't see the SST still. See, you don't see the model. Model is a sex model. Residual you see. You don't see the total yet. Okay, we come to that one later on. Okay. In this output above, which row is the error left over after fitting the sex model? The row that says the residual for sure. Error left over after fitting the model. See, error left over after fitting. See, because of this fitting, you have this much of this is good. See, this well fit. See, this one. Why do you think the sum of square for the empty model is greater than that of the sex model? Why do you think the sum of square here means the sum of square residuals? Okay, residuals in the empty model are compared with the sex model, because the sex model explains more variation. There's a leftover, there's a less leftover from the variation. They explain more variation. See, they explain, see, less variation, less leftover. Less leftover after the explaining that the variation by the model, this much has been explained. See, this is the amount that been explained. This is the amount being explained by the model. This is the amount being, not the leftover. This is the amount, sum of squared residue, sorry, sum of squared, the amount of variation, sorry, we call the variation, amount of variation explained by the model. This is the amount of variation left over after explaining by model. See, leftover is 28. In the beginning, it's not 28, it's 82. This is the leftover of the variation left over after explaining that one. See, after explained by the model, still you have a huge leftover. This much been leftover, not been explained. This much has not been explained. This is the leftover. See, see, that's why they say it has gone down. See, more variation. There's a less leftover variation. See, leftover variation is less. See, leftover variation, 28. This is the explained variation. This is the unexplained variation, another way. That's why we call that leftover. Explained variation, explained error, unexplained error. Unexplained error due to several things. You know that one. Unexplained error, we discussed that one in the beginning. Unexplained error comes due to certain things. One is intrinsic. The other one comes from that when we're going to do the sample. Can you remember? We discussed that one in large scale at a certain point. How the variations are come. Then the within the system and all kind of a variation we discussed in the beginning. Okay. So anyhow, this is the leftover. That we are kind of okay. That's why we're gonna see that from the pre, with the aid of pre, we're gonna see how much. See, model has explained how much with respect to that unexplained coming from the other one due to the total unexplained variation. How much being explained? 65%. That means it's getting better. It looks like a better model. In another way, down the road, you're going to call this one another name for this one. Correlation coefficient. No, copy the determination of coefficient of determination. Coefficient of determination means you're going to determine whether this model would be the best model by looking at this number, which is this number, which is close to 1 is far better. 0 is the worst model. In the middle 0.5, that's okay, but anything more than 50%, kind of okay. But if it's higher the value of this one, far better the model would be. If this model doesn't work, we pretty much, if this explanation is not enough, if this variation not been explained by this model, you're going to move on to another model, or you're going to add another variable. The variable that already you included, gender, is not enough to explain the variation in the thumb length. You are thinking you should going to add another variable. If that variable may be quantitative or qualitative, doesn't matter. Because down the road we're going to talk about the mixture. But at this the primary stage, what we're going to do, we're going to explain that one through only one variable. By this number is playing a heavy role. This is very critical. This is called another name. This one has a proportional reduction in error, or we can call the coefficient of determination. That would determine that one, how this variable going to be accepted or not. Okay, that kind of broader discussion we can have even in the next class. But for time being, we can look at that one. That's why they say that unexplained variation or the leftover variation is less. Leftover variation is 28 now. Earlier 82. See, look at the residual. That's why we call the residual. Residual means you cannot explain that. It is an error. It was erroneous. That's why we cannot explain. The error comes due to that intrinsic and then extrinsic matters. We discussed that one, how they're going to come from the sampling error, human error, okay, that units error, so many due to that one, errors that we're going to have that. But if you use the Y bar only to explain this one, that's not a good model. See, very huge, massive amount of these variations not been explained, left over. At least due to this one, they have explained 54. Still leftover is less. And the empty model explain less variation. See, empty model explain less variation. That's true. Empty model explain less variation. It didn't explain anything at all. See, less. See, explain less variation, more leftover. Because of that, less has been explained. Less variation has been explained, so that it's going to the leftover with the higher variation. But when it's come to the sex model, it's going to explain more variation. In that way, the leftover of the variation is less. Okay? That's the reason that they have the different sum of squares. See? So the empty model is greater. See? The red square depict which of the red square. I'm gonna get back to this one. Okay, this one, yeah, there's something based on this. Let's go. See, as I mentioned over here, now I'm gonna run instead of supernova. I really need to see proportion reduction in error. That now they are coming for that one, comparing two models. Okay, two models here is the empty model and the sex model. Okay, those two models. And even though that sex model not going to work, that you move over to that another model, you're going to add another one. Then it's going to be instead of 2 groups, 3 group model, like or another variable like that. Okay, you can do some adjustment. But anyhow, you're going to use not the nova, now use the supernova in order to see get even the empty model. See, sorry, the total. See, total to get the total. See. Get the total. Last time total was not displayed. This part not being displayed. When you run Nova, it displayed up to here. But if you need the full scale of the picture, like a P, F, MS, DF, everything, that will be given by running that supernova. But if you do the same thing for the null model, there are nothing here. You can remember model from model. See, error coming from the model. Error come from the empty model. See, error comes. See, error has been reduced due to this introducing the model. There's no such discussion in the empty model. Everything going to go to here total. Now they call the total as L2. Sum of the squared residual for the empty model is nothing but the total sum of squared sum of squared for the empty model. You can put the two names for that one. So we're gonna run the supernova. See. Go to tiny empty model, run supernova. You should get that table, Nova table, full table, ANOVA full table. See, 82, 5 degrees of freedom. We discussed that on large scale, and 82 divided by 5, 16. See, it's going to display even the proportion of reduction in the proportional reduction in error and p-value. We discussed the p-value, what the p-value. I discussed f-value, p-value, the similar fashion. See, similar fashion. If you do the same thing for this other model, so tiny sex model, but sex model. I'm gonna show. Oops. Oh, there's no dot. See, as I mentioned over 5428. If you add these to sum of squared of model plus the sum of squared of a residual or error, that would give you sum of squared total. SST, SSIE, SSM is another name. This is coming from the empty model. Or this is the sum of squared residual coming from the empty model. Sum of squared coming from the empty model. See, sum of squared residual coming from the empty model. Sum of squared error coming from the empty model. This all are error, SSCs, okay? Those all are SSCs. This is a sum of squared residual from the model. This is a sum of squared residual reduced by the model. See? Reduced by the model. That's why it's called SSM. It has another name. See? It has another name. And this is the sum of squared total. That means that this is the sum of squared residual from the empty model. This is the sum of squared residual from this given sex model. This is a sum of squared residual being reduced by the model, by the new model. Model means that a two-group model or gender model or sex model. Okay. So that's what they were talking about here. That means that this is something I'm talking about here. That means that if I'm gonna write this one clearly, see, let's see. See, this is the source. Source means like a what is? How could you get the variation? Okay, source. I have three sources. One is okay. This is sum of squared model, sum of squared error, and then we have sum of squared total. See? This is nothing but SSC is nothing but sum of squared error of the complex model. Complex means a two-group model. Okay, I'm gonna call that one complex model. Complex model. Sum of squared error due to this complex model. This model. This is what? Sum of squared error due to what? Simple model. It's nothing but sum of squared error due to empty model. Empty. It's nothing but sum of squared error due to null model. See? I'm going to write like this. See? Complex means sum of squared error, same thing. Error due to same thing. Okay, another name you can say two group model. See? Look at sum of squared total is nothing but the sum of squared error in the simple model, sum of squared error in the empty model, sum of squared error in the null model. SSE in this display, whatever the value they display over here, nothing but, which is this 182. This error is 28. And the SSM is nothing but SSE, see, SSE in the simple model minus SSE in the complex model, see, which is simple model has 82 minus 28, which is 54. See? That one also that sum of square. See, it's nothing but if you're gonna write everything with the aid of the empty model, or the model that even though that you have a two-group model or complex model, still it's all about the residual, all about the error. See, yes, error. See, that's what we were talking about here. See, these two add to this one, no, this one minus this one give this one, no, this one minus this one give you this one minus this one give this one. If you add the degrees of freedom, they're going to go to 5, as I mentioned over here earlier, 5. So see, this minus this will give this one, this minus that will give this one, and this is not the case. Okay, don't add these. They don't add. This divide by this one, you get this. This divide by that, you get this. And this divide by this, you get this. And on the other hand, this divide by that, you get that. Then how do you get this one? Which divide by which? You can remember. Pre is nothing but proportional of explained by the model. See? Pre is SSM divided by SST. SSM divided by SSM divided by, which is this divided by that. See? This divided by that. See? So then if I write this model, okay, and show to you, see? So you have a model. I'm going to write first and then show you model, and then we have an error. Okay, I'm going to show this one. Model, you got 54. We calculated 54. You know how we got sum of square model. Then you got 28. You know how we got that. Then we have a total, which is 82. We know how we got that. Then we have a degrees of freedom. We know how we got 1. We know how we get 4. We know how we got 5. And then we have a mean squared. Mean squared is nothing but SS divided by degrees of freedom from their respective values. So this is, see, this value is nothing but you can say SSM. This value is nothing but you can say SSE. This value nothing but you can say SST. So this value is nothing but degrees of freedom of M. This value is nothing but degrees of freedom of E, degrees of freedom of T. So this one is nothing but mean squared of MSM, mean squared model. That means SSM divided by degrees of freedom of M. So 54 divided by 1, which is 54. Okay. Then the other one, mean squared error, which is sum of squared error divided by degrees of freedom of error, which is 28 divided by 4, which is 7. Then this one is nothing but mean squared total is sum of squared total divided by degrees of freedom of total, which is 82 divided by 5, 16.5. See, so that one up to that point, up to here, here, here. Then you saw F. I'm going to bring this one to the here. Okay. So this is model. This is model. This is error. This is total. So the next one is F. F is nothing but mean squared model divided by mean squared error. Mean squared model divided by mean squared error, which is 54 divided by 7, which gave you 7.7143. Then you have a pre is nothing but mean squared, no, sum of squared mean divided by sum of squared total. Sum of squared mean is nothing but 54 divided by 82, which is 82, which is 0.6585, 0.6585. Then you have something called P. P is nothing but the P value. P value is the probability that F is greater than, if you want, I'm going to call this an F naught. Okay, F naught. That's nothing but F greater than F naught, which is 7.7143. In this case, it's going to be 0.0499. That's how we got all these values. See, from those calculations. And on the other hand, even f can be explained in terms of pre as well. See, can you remember we had another formula for f? See, you get the pre, you get the df. If you plug in into this one, you should end up with the same thing. See, if you have a pre, that means the formula again f should be same as what we saw over here for the 7.7143. Pre, if you add to pre which is 0.6585, okay, pre divided by degrees of freedom of the model, which is 1, and 1 minus 3.6585 divided by degrees of freedom of error, which is 4. So you have if you go to calculate and then you're gonna do this calculation, you should end up with the same f value that you ended up with, 0.6585 divided by 1. You don't need to divide by 1. Divided by 1 minus 0.6585 again divided by 4. Then you get 0.4820, but 0.4820 is almost like a 0.49. 0.4820. If you keep this one to 2 decimal places, sorry, 1 decimal place, 0.40, oh sorry, 48. The other one we got the 450, and the 50 means like 0.05. See, sorry, no, this is not right. Okay, no, this one. I wrote the wrong one. 0.6585. 0.6585. I'm looking at the wrong one. Okay. 0.65. F value is 7.71, not the one. Sorry. 0.65 pre value, pre divided by degrees of freedom of model 1. 1 minus 3 degrees of freedom of error is 4. So I'm gonna have 4 times 0.6585 divided by 1 minus 0.6585. Yeah, 7.71. I'm sorry, that this one is nothing but 7.717130. So if you round this one to 2 decimal places, 7.71. So that's the same thing we had for here, pretty much same thing. See, 7.71 up to that 2 decimal places. 3 places not going to be same because of this rounding, because they have done the intermediate rounding. If you do the intermediate rounding, it's going to affect to the, rather than that you are supposed to plug in that the values as it is. Normally we don't do the rounding in the intermediate steps. Because of that, it's going to affect to the final answer, and then we're not going to have the same as what you see here. Anyhow, they close. See, pretty much they were okay up to that third significant figure. So that's partitioning. I talk about this one already. I don't think that we have to go for that one again. See, that's why they say partitioning means 54. Partitioning means decomposition. See, that's the same thing I talk. I talk this one in detail. I talk this one in detail, very detailed. Sum of square total is how much? 82. Sum of square model is how much? 54. Sum of square error is 28. We had that heavy discussion. This is due to empty model. I think we discussed this one in large scale. So SS total, if you want to SS total, how do you get the SS total? How do you get that one? The codes are very important. Okay. So how do you get the SS total? See, sum of square total. Go to sum. See, sum to empty model. See, sum to empty model. See, sum to empty model. See, it's sum to empty model. That's right. See, that's the total. Y to Y bar. Sum to empty model. This one, sex model to empty model. This one to thumb to sex model. Okay. In another way, that the way that I wrote over here, I'm gonna go back to here and this one. Okay, this one this is what I'm gonna add something to here. See, add something to here. See, here. They say that this is SS total is in the context of this what given is sum to, see, look at this one. That one we can say thumb to empty model. See, this is thumb length, this is the empty model. See, thumb to empty model equals the other one sum of squared of sex model to empty model. See, again, see, empty model. This is empty. See, empty model. See, this is coming from sex model. I mean, like all together. I'm talking about all together, whole thing. Okay. So that one is nothing but empty model. The other one is this one, this model to empty model. Model plus last one is what? Thumb to sex model. See, thumb. This is thumb length. See, this is a thumb length. Thumb. This is thumb. This is also thumb. See, you know that. The other one is sum of square to what? Thumb to sex model. Like that. You can look in at like that way too. Sum of square in the context of this given problem. See, that's how these three terms. See? There are three terms we can explain in the. See, this is a one term. This is another term. This is another term. Or this is one term. Model error. So that's the same thing here. See, total means come to empty. So we had this discussion. Then they were looking for go sum. See, you can get the error reduced. See, you can find that one. How could you gonna find that one using that setup? Okay. So you have a thumb to empty model, sex model to empty model, thumb to sex model. So we need something first. We are looking for the tiny fingers, error reduced, error reduced, error reduced. They call the error reduced for the model. There's another name for the model, error reduced. SSM, they're gonna call SS sum of squared error reduced. That's the same thing. That's the same thing. Error reduced. That means they are looking for. You go to the predicted value. You go to the empty predicted value. See, error reduced. Model is nothing but model. I'm here. Model. Model is nothing but thumb to sex model. Sex model to empty model. Sex model means like a predicted value from the sex model. So a predicted value from the empty model. See? Sex to this one. Sex to empty. Model means predicted. Predicted minus this one. And then what? See? Error reduce. Let's create a column of error reduction. Add code to sum up to the squared error. And then you need the squared error. You can square that one. So tiny fingers, error reduced, square. Another way to get that, and then sum them up. This creates a column that the same way over here. Let's try this to see if we get the 54. Okay, and then SS model error reduced from the supernova table. Try putting all this together in the data camp window below. Okay, so you have error reduced. It's the model SSM. I'm trying to get the SSM. I find that difference, which is called error reduced. In this one, it has to be squared, and then sum them up. You go to the model, see, X model to empty model. See, X model to empty model. Get the difference. Get the difference. This is nothing but y bar f and n minus y hat. Another way you can say y hat. Same thing. That's the same thing. Y hat. Y hat minus see y bar. This is y bar. Or in these terms, you're going to write in this term, you can say x minus this one. See? So get that one and then square and then sum them up. Now let's try this to see if we get 54, the SS model error reduced from our supernova table. When you get that one, try putting all this together in the data camp window. See? So this one, empty credit. Then you add the code to sum of them, the sum of the squared error reduce. Okay, then you're gonna get this one. You're gonna get that one. You don't have to do like this because supernova will give that one for sure, but still we're gonna check whether we are doing this one is right. It's club 54. It's 50. See? Predicted to predicted. 54. The proportion of reduction, I explained that one. I gave this one. See? I explained that one in this way too. Another way of writing. Pre even that you want to write in that way too. I'm going to add that one too. Pre SST SSM. So see this one here. Pre, I'm going to get this one now. See pre here. Another way that SSM is nothing but SS total minus SS error over SST. That's another way to write it too, if you want. Or you can write this as 1 minus SSE over SS2. That's the same thing. Then I find the connection between F and pre as well too. 1 minus like that. 1 minus SSE over SST is going to give you the same thing. See, that's what we were talking about here. See, if you have a two model for the sum outcome variable, one more complex than the other one, which will have the larger sum of squares error, which one has the larger one? Not the complex one, simple one. Simple one is the empty model. Always a simple one has a larger sum of squared errors that has to be reduced by introducing that complex model. Okay, that's the same thing that we wrote. The same thing. Pre-ranges from 0 to 1. A proportion of the total cannot go beyond the total. See, it's between 0 and 1. Pre is always between 0 and it's a proportion. Proportion is always between 0 and you know that one. And pre can be thought of as the percent of the explained variation. See, it's a physical meaning means what? How much variation being explained by this model? How much variation being explained by this model is the pre. Variation of the percentage of variation explained by the model. See, this is nothing but percentage of percent of variation explained by the complex model. Complex model. What is this? Okay. Complex model is pre. See, that's pre. That's pre. See? It's a model that one. How much being explained by this one. Because of that, it has another name, free coefficient of determination. Coefficient of determination, that's another name. It will decide whether this complex variable model would be better or not. See the pre 6.6 is a proportion of total error from the empty model reduced by the sex model. See how much being reduced by the sex model, or proportion of total error from the empty model explained by the sex model. See, two ways. See, proportion of total error. See, so this pre is playing a heavy role, massive role. Okay, so I'm gonna write it this one here for you to see very clearly that PRE. See, I'm gonna write back again. See, PRE is that proportional reduction. Proportional. That's the proportional reduction in error. Okay, it means proportion of total error from the empty model reduced by the this model, complex model. Okay, in the I'm going to talk about that particular model in this case. Or proportion of total variation, total error, or variation, total error or variation from the empty model explained by the sex model. It's reduced by that model or explained by that model. Okay. Or percentage of variation. It's the same thing. I see. Like that. That's the same thing. Please play in heavy role. Okay. Then if you need the B1 in this model, you can run the B1 and B0 separately. See, if you go to B1 and run that one, that would give you that B1 only. See, and B1 means the difference between the two means, male and female means. You can remember B1. It's a function. See, B1 function you can run. See, that would give you the value over here, the difference between two means, the males and female means. You can remember. In that tiny fingers, it's a 6, but in the full data set, see, total finger data set, the mean between the males and females, total finger data set, we have 157, I think, data points. So then 6.44, the gap. See, you can go and run with the B1. See, that would give you, or you can save this to somewhere and then put it inside this argument. That will give you that one. See. Then they say that how do you get this, so that the pre is already there. There are several ways. Measure the effect size. Effect size means like a what means like a, that's a little bit important one, that after doing this one I can stop, and then if the leftover that I can do to another video. Okay, but I'm gonna see I think only 2-3 pages. We don't have that much after this one. By averaging, and then the ratio, I explained the ratio already, but I can go through detail and make like another video. Anyhow, I'm gonna just do that page and then we can stop here. Okay. On the 3 group. Yeah, you see, measures of the effect size. See, there are several ways you can get this done, by looking at the B1, by looking at pre, by looking at Cohen's D, how their D, see Cohen's D. See how the D can be calculated, this kind of a thing. Okay. So little bit, let's go through this one real quick. So far we have been talking a lot about the model using sex as the explanatory variable. See, that's the explanatory. The sex model is an example of what we could call a two-group model, because there are two values for sex in this data set, and thus we do groups of data. We've been thinking about trying to measure how good or bad our model is, but there's another way to think about this. See, given that an explanatory variable has an effect on an outcome variable, thumb length, how big is the effect? If you feel like that by introducing this new variable, X variable, which is gender in this case, that if it's going to affect to that thumb length, how big that effect would be? How could you going to measure the effect size? Effect size. We call the answer to this question effect size. We haven't used the term effect size up to now, but we have in fact presented two measures of effect size so far. By looking at B1, see, the most straightforward measure of effect size in the context of the two-group model is simply the actual difference in means between two groups, male and female outcomes. You can easily get that one by running this one LM, when they're going to show you here that this is B0, this is B1. See, there are parameter estimate from sex model. Which number show you the difference in means of the thumb length between two groups? B1, which is the difference between two mean groups, is 6.4. Or you can go straight and get that. In our data set fingers, we can see that the size of the sex effect is 6.44 millimeters. Males on average have numbers that are 6.44 millimeter longer than females. That's what it means. See, that means on average, male would have a thumb length 6.447 millimeters longer than the female. See? That's what it means. See? That's one way to that. Have a look at it and see what the effect size would be by introducing this gender, by looking at B1. But if you want B1, you can see parameter estimating the question came from the running this one. Another more direct way to find B1 estimate, in this case, the mean difference between the two groups, is to use B1 one shot. See? That's another way to look at it. Or you can go ahead and then run in this one and get the value, or you can run this one and then get the B1. Okay. See? That's pretty much, if you run this one, why should you gonna have this one? But that's another way of doing that one for some situations. See? That's the same thing, 6.44. That's the effect size. That's the way how you're gonna see that how my gender would affect to that one. What would be the size of the effect? Let's see, you can give it quantify that size, like a 6, see, around like a 6.4 millimeters. See, about that. See, they have a longer, and the male have the longer, 6.44 millimeters longer than female's fingers. See? Can quantify. Another way to look at it, please see. By introducing this model, how much been explained. See, we already run this one. We know how to get the pre. See, we did all kind of these things. Okay. Pre-explain that how much error being explained by the model. See. We had that one. See, when we discussed about this one. This is for the total fingers, but we did that one for the regular one. See, look at pre, so almost like 11% being explained. See, not good. See, the model explained only 1,334 out of 11,880. This much not being explained. It's not a good model. See, only 11% being explained by the total. Out of total, the model will explain. That means 1,034.203 divided by 11,880.211 is 0.1123. That's not a good model. Only 11% being explained by that model. That means you have to do some adjustment. Okay? Another way to look at this one is third measure of the effect size is applied especially to the two-group model is called the Cohen's D. Cohen's D is related to the Z-score. Recall the Z-score tells us how far an individual score is from the mean of distribution in standard deviation unit. But Cohen's similarly indicate the size of the group difference in standard deviation unit. You're not going to go to the look for that mean. Instead of one mean, you're going to get the difference of the two means, that male and female, and then it's going to be divided by the standard deviation. You're going to give that one in terms of standard deviations. See, standard deviations. It's going to be given by standard. See, this is a male minus female mean, or the other way around. See, that would call you this one D. If you try to calculate Cohen D, you will soon encounter question: which standard deviation should you use? The standard deviation of the outcome variable for the whole sample, or standard deviation for the outcome variable within the two groups, for the male only or the female? Which standard deviation? Standard deviation for the grand standard deviation, or for the male standard deviation or female standard deviation? Because of that one, they came up with some kind of a remedy. See, there's a remedy. One remedy is, instead of using that S, you're going to use something called the pool standard deviation. How do you get the pool standard deviation? You're going to multiply degrees of freedom of each group. See, each group, degrees of freedom of each group, S1 plus S2. And then you're going to add degrees of freedom of these two. So that means, see, you can easily get this one, but the degrees of freedom of, degrees of freedom of each group. Let's say a female group. Can you find the standard deviation of female group? Yes, you can find it. Can you find the degrees of freedom of that group? See, you can find it. See? So this one, then this one, okay. The solution is a weighted average of the two standard deviation, weighted by the number of degrees of freedom. It has been weighted by number of degrees of freedom. You not simply get the standard deviation plus standard deviation and divided by the total number of observations. See, you cannot figure out which has to be placed over here. To come up with like a middle ground, whether go to the grand standard deviation or female grand standard deviation or male standard deviation or which one, we have three questions ahead of us. Instead of that, we're going to say, don't use none of them. Let's use something called the pool one. Let's pool it. Let's weight that one. The standard deviations are pooled, weighted by the degrees of freedom of each group. This solution is to see, just average two standard deviation. This works fine if the two groups are the same size. See? If they are same size, you can average it. But imagine the situation where the sample size in one group is 100, but in the other only 10. If we average the two standard deviation, we are assigning the same importance to the estimate of standard deviation based on the group of 10 as to the estimate based on the group of 100, which doesn't seem right. We should have more confidence in the estimate based on the larger sample. So that's why we're going to get the weighted average. How do you weight? Weight by the degrees of freedom. Standard deviation, normally if the sample sizes are the same, you can add these two and divide by 2. It doesn't work here. They said weight by the degrees of freedom. See, degrees of freedom of this one, of the first group. The solution is to use the weighted average of two standard deviation, weighted by the number of degrees of freedom in each group. This is often referred to as the pool standard deviation, and this is what we use to calculate Cohen's d. The pool standard deviation is calculated like this: df1 this one. Another way to find the pool standard deviation is to simply take the square root of the mean squared error. See, that's another way on your supernova table. Mean squared error, recall, is simply the sum of squared error divided by the degrees of freedom for error, which yields the variance estimated based only on the variation within groups. See, another way to find the pool standard deviation is to simply take the square root on this one. So they say that either you go to this one, see, I'm talking about this one, either standard, see, so I'm over here, see, Cohen's d, okay, I'm gonna quick finish this one, okay, but I ran out of ink, okay, I'm gonna put a new okay, I'm gonna take this out, a new one. Okay, see, Cohen's d. Cohen's d, we have the Cohen's d is the distance between the difference between y1 female minus y1 male divided by s. So this s should be replaced by y bar f minus y bar m is pooled. See, instead of that one, they say you can put y bar f minus y bar m can be do like this way. They say do like this way. So the degrees of freedom for female divided by s of female plus degrees of freedom of f times standard deviation of that guy divided by degrees of freedom of females plus degrees of freedom of males. These are for males, okay, not the model males. Okay, see, like that. Or they say you can do d y bar f minus y bar m whole 1 divided by mean squared error and take the square root on it. That's another way to look at it. Or simply you call that one y bar female minus y bar male divided by, it's been called the root mean squared error. See, root mean squared error, that's the same thing. See, that's why they say instead of that pool one, there's a best estimate. The best estimate for that one is, see, best estimate for that one would be the root mean squared error. You can use it, or you can use the degrees of freedom of female. So the standard deviation you can easily find. Degrees of freedom of this one is nothing but number of elements in that one. Like in this case, in our case, we can say 3 minus 1. Okay, 3 minus 1. This one also. Oh, I'm sorry. This one male. Okay, male. Made a mistake. Male. Males. Okay, males. Degrees of freedom of males. Weighted by this one, which is 3 minus 1. Always this degrees of freedom here. See, standard deviation you can easily find for males. Okay, and divided by degrees of freedom of males. See? 3 minus 1. Sorry, 3 minus 1. Okay. Like that. So the root mean squared error, you know mean squared error. You can remember mean squared error in this case. Mean squared error. See, see mean squared error. See, mean squared error. 68.039 divided by, so take the square root on that one. That would give you that. See, or you can straight go to, see, this one. See, and then calculate. See, Cohen's d for the model. That would give you 0.7815. See, see. So the y bar f. So let's say that if you have a Cohen's d, they ask us to say y bar f minus y bar m over, let's say I'm in the root mean squared error. That means y bar f is 59 minus this one is 65. You can remember. Is that 60, 59 and 65? I'm doing this one for, no, they are doing this one for the complete fingers. What's the mean of the, I don't think that we don't have that one. Okay, we don't have that one. I think that I can, but I'm gonna stop over here. I'm gonna get started from this page. Okay, go and do in detail and then upload into the system. Okay, do you guys have any questions? And then this is the last day of this class, and then make sure that you're going to turn in everything, that you have a time until that next Thursday, sorry, the Wednesday, or that take your time and finish it. And if you give me like early, I can put all the grades, all that whatever you have turned into that system, I have already received that one. Okay, even though sometime I didn't email it, I have received that one. Okay, everything I have with me. I'm grading everything, and then I'm gonna put the grade for your quizzes, homework, midterm test, and all the exams, final exams, everything. Okay, for the final exam, you know what the final exam is. It's everything, the chapter 7 end review questions. Okay, I'm talking about this one going to be your final exam. Okay, this is your final exam. Okay, so okay, we have two sets. Okay, at least do one of them. Okay, at least do one of them, or if you want, you can do both of them. I'm still gonna give the full credit for that one. Okay, if you need more time to, because sometimes if you haven't done that previous uh, assignments, that if you get stuck over here and in a hurry to try to do that one and you're running out of that one, make sure that at least do out of these two for your final exam, either this or that, or both of them, doesn't matter. Okay, then starting next Monday, we're going to start from this discussion. We continue. You see, each week we'll have only one chapter. That's easy. See, 9 for second week, 10 for third week, 11 for the fourth week. We're done. Not the 12 one. 12 this we just mentioned. Pretty much the same format, same fashion, same time, same book, same instructor, but maybe most of the same student, and like that. Okay. So if you guys have any question on anything, just let me know. If you don't have, I'm gonna just wind up over here and have a good night, and then stay safe and be well. Okay. See you next Monday, and then or that if you want to have like a one-on-one session, just let me know anytime. I'm ready to help you out. Okay. Take care. Have a good night, and thank you very much. Thank you. Okay. Thank you. Thank you. Have a good night. Thank you very much. It's recorded.